Early in the course, we argued that a rotation is a linear transformation. Later, we showed how to compute the matrix that represents that linear transformation. Finally, we ended last week by talking about matrix-matrix multiplication as representing the composition of two linear transformations. In this video, we bring all these ideas together by looking at how to compose two rotations in 2D. As if by magic, the law of sines and law of cosines, which you learned in high school geometry, result. Recall how to visualize rotating a vector in 2D. We will denote the transformation that performs this rotation with r sub theta, so that rotating a vector x through an angle theta yields the vector r sub theta of x. Remember that the rotation can be represented by a matrix that involves the cosine and sine of the angle theta. Now, we can take the result vector, let's call it y, and rotate it through an angle rho. The result of that is given by r sub rho of y, and that rotation can be represented by a matrix that involves the cosine and sine of the angle rho. Rotating vector x first through angle theta and then through angle rho is an example of the composition of two linear transformations. The result is r sub rho of r sub theta of x. Next, we illustrate that we could have just rotated the vector x through an angle theta plus rho to yield the same result as first rotating through angle theta and then through angle rho. Now, let's manipulate all these insights. We start with vector x with components chi sub 0 and chi sub 1. We rotate this vector through angle theta. We know that this yields the same result as multiplying the vector x by the matrix with elements cosine theta on the diagonal and minus sine theta and sine theta above and below the diagonal. If we take the result of rotating x through angle theta and rotate it through angle rho, we can alternatively take the result of the matrix vector multiplication and multiply it by the matrix that represents the rotation through angle rho. But rotating through angle theta and then through angle rho is the same as rotating through the angle theta plus rho. That rotation can again be represented by a matrix that involves cosine and sine, but now taken of the angle theta plus rho. What we learned at the end of last week is that we can drop the red parentheses. We can then compute the matrix that represents the composed rotations by multiplying the two given rotations together. What we conclude is that the matrix that represents rotating through angle theta plus rho is equal to the matrix that results from multiplying the matrix that represents rotating through angle rho times the matrix that represents rotating through angle theta. Now, let's put this all together. If you focus on the top left element in both matrices, you find how the cosine of theta plus rho relates to the cosine and sine of theta and the cosine and sine of rho. Similarly, if you focus on the bottom left element of both matrices, you find how the sine of theta plus rho relates to the cosine and sine of theta and the cosine and sine of rho. What we have just justified through matrix-matrix multiplication are the law of cosines and the law of sines, which you had learned in geometry class. So, what do you learn from this lesson? Well, if you happen to forget the law of sines and law of cosines, but you remember how to create matrices from basic principles, and you remember how to multiply matrices together, then you can simply rederive them by knowing how to compose rotations and multiply matrices.